All right, let's get started. Good afternoon, everybody. Welcome to another wonderful afternoon of organic chemistry with your host, me, Dr. White. Now, one thing I should warn you, if I seem a little off my game today, not my normal exciting Dr. White self, that's because Dr. White is suffering from junk food overdose. You saw the big football game, and also you saw the big soccer game. Soccer, Manchester City beat Liverpool. By the way, I've been in both cities, Liverpool and Manchester. I worked in Manchester for a while. Uh, that was an awesome game. Then later on, Super Bowl, I have to admit, I was rooting for Brady to win another ring. Yes, I was. Wow, what a quarterback. All right. A couple things I like to talk about. Excuse me. Don't forget, this Wednesday, the lab we did, the melting point lab last Wednesday is due. Please upload it as a single PDF file. If you don't have a scanner that can make a PDF file, I have on D2L files how to use it. There's one app, Cam Scanner, for your phone to do that. And a student was telling me there's another one this morning in my other class that's called Scanner. And either one, well, I don't know about the second one because I haven't tried it. The first one, I know a number of students have worked successfully, will allow you to make a PDF file. If you do not have a printer, last November, my printer died and it took me a while before I found the HP I have over there. If you need a new printer, email me and I'll give you the particulars. I got this one over here from Staples. It was $199 plus tax and shipping was free. So they drop it off right at your door. Such a deal, which in this environment isn't too bad. And if you don't have a printer, take the file, read it. You don't have to rewrite all the lab. Just parts where you have to put data in, you write on a piece of paper. Then the questions you have to answer at the end, you put one, don't rewrite the whole question, and put your answer down and convert that into a PDF file. And for both ways, please write so I can read it. It always helps. All right, any questions before I start? All right, let's get going. Let me first clean up a few things. All right, everybody see hydrogenation of alkynes on your, thank you, thumbs up persons or people. All right, last week we were going over alkanes and alkynes chemistry. And remember, an alkyne is a triple bond, 3 lines. Each line is 2 electrons. Each covalent bond is always 2 electrons. And a triple bond has 2 pi bonds and 1 sigma bond. And you should know that. Just to remind you, a double bond, again, each line is a pair of electrons. It's 1 pi bond and 1 sigma bond. And that's quite important. You should know that. And I showed you how you can break pi bonds real easy. And organic chemists use the term bracket, excess, letters X and S, close bracket, meaning excess, the word, meaning you have all the hydrogen in the world that will react with anything hydrogen will react with, because organic chemists are lazy. We don't want to balance equations unless we have to do it. Remember, R is anything with carbon, hydrogen, just like X and Y and Z in math, any number, integer, positive or negative, that you could use in an equation. And if I were to ask you, give the organic product or products for the following, and Dr. White's going to help you out on this one. And why don't you try that reaction? Give the organic product or the products for the following. Remember, on test, you're not going to have these general reactions. You have to memorize them. And the best way to memorize them is writing them down 5 times and saying them, and you'll learn it. Also, do the practice problems. They'll help. You're doing organic chemistry. And it's fun. When you're done, give me a thumbs up if you can. All right. Is everybody done? Going once, going twice, slowly moving my pen to do this. All right, let's do it. When you look at a molecule, you should always look for what's different, what's not carbon, what's not hydrogen atom, or what's not a carbon-carbon single bond, triple bond. Triple bond, what are we reacting with? Hydrogen excess and platinum, which is a catalyst. And the general reaction is you break 2 pi bonds, and each carbon of the triple bond gets 2 hydrogens. Do you break carbon-carbon single bonds? No, you don't break them. Hold on. Am I losing here? Oh, no, don't look. But anyways, you don't break carbon-carbon single bonds. Never except in combustion in my class. That's when you burn something, and this isn't it. So I have 3 carbons. I better end up with 3 carbons. Now, the 2 carbons that were my triple bond, notice I broke both pi bonds, and just like I did here, and each one gets not 1, but for each pi bond gets a hydrogen, 2 pi bonds gets 2 hydrogens. And I know how to put in the hydrogens, and there's your answer. Now, if you wanted to write it like this is probably the world's most expensive way to make propane, you could, but I would say leave it like this because it's one less step for you to do on a test to mess up, which is always good to do less steps to mess up. And by the way, I don't know if I told you, I'm this close to the person who grades the test, me. So you can do it either way. Next, I talked about halogenation, and halogenation is similar to what you learned with a double bond. You take a triple bond and react it with excess halogen gas, and again, we're using the terms, the letters X and S in a bracket to say you have all the halogen in the world that will react with anything halogen will react with, excess. And what happens is you break the 2 pi bonds, remember triple bond, 2 pi bonds, 1 sigma, you break pi bonds, but not sigma, single bonds, and each carbon, because the 2 pi bonds, gets 2 halogens. And remember, X here can be fluorine, chlorine, bromine, or iodine. And I went through this. And why don't you try this one out on this beautiful but cold Monday after the Super Bowl with Dr. White suffering, really suffering from junk food overdose. If my skin looks a little orange, reddish orange, that's the Doritos. I love Doritos. Luckily, I didn't also buy, which I should have, but I didn't. My another favorite is Frito-Lay's onion, sour cream and onion potato chips. Those and Doritos just seem to disappear from my house immediately. They just evaporate. And when you're done, give me a thumbs up. All right, looks like everybody's done. Let's do this. Look at a molecule, look for what's different. What's not carbon, what's not hydrogen, what's not a carbon-carbon single bond should get your attention immediately. Ooh, a triple bond. I'm reacting with excess iodine, which is a halogen, and immediately I know this. This is an awful looking triple bond. Let me fix it up. This is a better one. Remember, X can be for this reaction fluorine, chlorine, bromine, or iodine. And what happens is each carbon of the triple bond gets two halogens. Do you break carbon-carbon single bonds? No. So I have 1, 2, 3, 4, 5 across, and my answer will be 1, 2, 3, 4, 5 across. On this carbon, I have a methyl group. It's still there. Here are my two carbons of the triple bond, which are these two carbons, which my general reaction tells gets two halogens, in this case, iodine. And I know there are 4 bonds to carbon, so I can put in the rest of the hydrogens. And that's your answer. And that's how you do double bonds and triple bonds. Well, this is triple bonds. Oh no, guess what? We have finished a chapter. There's a couple other things I wanted to go through that will be on test 1. But before that, it's time for a public service announcement from your host, me, Dr. White. I think I might have mentioned it. If not, I'll mention it now. A number of years ago, I created a method that eliminates test anxiety. And by the way, organic chemistry for some students causes a lot of test anxiety. And that's a very serious problem. And this method I developed eliminates it. Oh, by the way, you can use it for other subjects too. And also, if you're going into a high stress situation like talking to the CEO of a company and other people, that's high stress. Wednesday, I will teach the method. I don't have a good name for it. I just call it the method. Wednesday, beginning of class. I will eliminate it from the video that by the way, I've been posting stuff up to date on YouTube channel. I'll eliminate that because someday maybe I'll try and sell it, make some money, which is a good thing. So come to class on Wednesday, and it helps students. If you don't need it, well, you don't have to use it, but it's amazing. I've had Chem 170 students, also general chemistry students, that going from D and barely C students or even Fs up to A's and B's. And it just eliminates their test anxiety. And I'll do that on Wednesday. All right. Now, Let's talk about two things. I didn't do slides for material for test number 1. Now, when we talk about molecules, most of the semester, I will stick to, let me real quick. Everybody see my whiteboard? Thank you. I will stick to molecules that have one functional group. But in real life, you have molecules that have more than one functional group. And let's look at an example. And when you have a double or triple bond, when they're separated by more than one carbon, then each double bond or triple bond acts like it's alone. So if I were to take, this is called a diene, di-2-ene double bond, which I'll never ask, but this you should know. If I were to do this reaction, what happens? Well, you look at a molecule and look for what's different. What's not, and this should be a 2. Somebody should have caught me on that. Anyways, look for what's not carbon, what's not a hydrogen atom, or what's not a carbon-carbon single bond. Oh, look, a double bond. No, there are 2 of them, and they're separated by more than one carbon, so they react independently. Now, if you notice, I've done excess. That's because I'm a lazy organic chemist. I thought you only use that for triple bonds. No, anytime you don't want to balance something and you want to have as much reagent as you want, you use this designation. So this means I have enough hydrogen to react with anything that hydrogen will react with. What will happen? Well, double bond, hydrogen, catalyst, and the catalyst can be platinum, palladium, or nickel. If you're in an industry like I was, you always use nickel because platinum and palladium is extremely expensive. Remember, double bond, 1 pi bond, and 1 sigma or single bond, which you don't break, but pi bonds you do, and each carbon gets a hydrogen. Well, if I look here, I have 6 carbons. Do you break carbon-carbon single bonds? No. So I have 6 carbons. If I look at this double bond right here, I break the pi bond and each carbon gets a hydrogen, my general reaction. If I look at this double bond, I break the pi bond and each carbon gets a hydrogen. They react like they're independently. And I know there's 4 bonds to carbon, so I can put in the hydrogens, which you need to do on a test. That's the 2, and I'm done. Now you could have written this one CH3, CH2, same thing here, but this is okay. And that's how you do it. So when you have a double bond or a triple bond separated by more than 1 carbon, it reacts like it's independent. Now, when it's only 1 carbon, there are a whole lot of other things I'd have to teach you, and that's a 2 semester, not a 1 semester organic stuff to teach. And why don't you try this one? Hopefully you're learning general reactions. I'm going to help you out in case you haven't learned it yet. You should. And why don't you try that one? I get to see everybody who's got their web camera on, your pretty faces. Thank you for turning it on, because I get to see your real people. That's not names on a screen. And also those of you have nice emojis, I get to see those too. And your names if you don't want to do either. Cynthia, you like that, huh? And when you're done, give me a thumbs up or look up and smile, or do none of the above, and I'll just have to guess. Oh, when you're taking a test, make sure you write clearly, because you don't want Dr. White to guess what you wrote down, because I can be 50 half time right, half time wrong. I try and guess right, but you don't want me guessing. All right, I think everybody's done. Let's do this. All right, if I look at this molecule right here, what's different? What's not carbon? What's not hydrogen? What's not a carbon-carbon single bond? Immediately I said double bond. Oh, wait, there are two of them. Now there's 1, 2, 3, 4, 5, 6. Do you break carbon-carbon single bonds? No, because I'm not doing combustion. If I look at this double bond, you break the pi bond, and each carbon gets a halogen. Now, why did I put excess when it's not here? Because I don't want to balance the chemical equation. Therefore, I have all the bromine in the world that will react with anything bromine will react with. One of those things is a double bond. And you'll learn more about that this Wednesday in lab. And here to these two carbons, which are these two carbons, I'll add, each one gets a bromine, because a double bond has one pi bond and one sigma bond, and you can break pi bonds real easy. Now, if I come over here, I also have a double bond. And there, same thing happens. Each one I add a halogen to. In this case, it's still bromine. And a halogen is one bond. So now I can put in my hydrogens, because I know there's 4 bonds to carbon. And there's my answer. And that's how you do it. Oh, let's do one more of these. These are fun. Now, on a test, I wouldn't give you this, but since I don't know if you had time because of the Super Bowl and also the Manchester City Liverpool soccer game, if you have a double bond reacted with acid and water, remember water is HOH, you break the pi bond, one carbon gets H, the other gets OH, and it follows Markovnikov's rule. The carbon of the double bond with the most hydrogens gets the other hydrogen, the other carbon gets the hydroxyl group, and let me make that H on the hydroxyl group look better. And have fun. What would be the organic product or product for the following reaction? 3 points each. And normally you don't do it because water is present, but I could have done this. whenever you add water, because it has such small molecular weight, you're always going to wind up adding excess. Most of the time. You can't control it, but and a catalyst, you just need a little amount, no matter what scale or how many you use. That's what they mean by a catalytic amount. And when you're done, give a thumbs up. Or if you have your video on, you can always smile. I'll give you 8.76 more seconds. 7.8, 8.2, 8.6, 8.6. Time's up, 7, 8.7. All right, look at a molecule. What's not a carbon? What's not a hydrogen atom? What's not a carbon-carbon single bond? Double bond. Over here, double bond. And what are we reacting with? Acid and water, excess. And what happens? Double bond. Remember, one pi bond, you break easily. One sigma or single bond, you don't. You break the pi bond. One carbon, remember, water is H and OH. One carbon gets the H, the other gets the OH. Follows Markov-Nikod's rule. The carbon of the double bond with the most hydrogens gets the hydrogen, and the other gets the hydroxyl group. If I look here, 2, 1, double bond over here, 2, 1. I'm talking about hydrogens. Do I break carbon-carbon single bonds? No. I have 6 across. And this carbon, I have a methyl. Now, this carbon has 2, this has 1, so the hydrogen will go there, the hydroxyl group will go there. This carbon has 2, this has 1 of the double bond. Again, the hydrogen goes to the carbon with the most hydrogens. Remember, the rich get richer and the poor get poorer. And I'll put in my hydrogens, so I know there's 4 bonds to carbon. And the hydroxyl group counts as 1. And that's how you do it. I wanted to cover that because this is real life. And that's really the beauty of functional group chemistry. When you have a functional group, whether 1, 2, or 3, if they're separated by more than 1 carbon, they react like they're alone. All right, there's something else I'd like to talk about. By the way, I should tell you, Dr. Wade has the fastest mouse wheel finger this side of the Mississippi or the other. So a good question. Remember, in my class, there's no such thing as a dumb question. All questions are good questions. Can I see that again if I pass by too quickly? Don't forget, you can also watch the video, but still ask, pull it back. All right, now, if you had a bachelor's degree in chemistry, organic chemistry, master's, or like I have a PhD, and you go to work for a chemical company or a company that needs organic chemists, no one will ever ask you when you get hired, if I take this and this and react it, what will I get? No, they won't spend money on that. They can look that up in a book. What they do ask you is, how do you make things? And that's the fun part of organic chemistry, but I'm biased because I'm a synthetic organic chemist. What are synthetic organic chemists? Those who have been trained to make things. Synthesis is a fancy word meaning make. So let's look at something interesting and fun now. And the question would be, what would I react with chlorine to make this molecule. Another way of saying that, and sometimes it may even be 4. Let me do a better A there. I can blame my writing on junk food overdose. Boy, did I. Doritos, all the good things in life, chicken nuggets, the good kind, salami sticks, Little Debbie cakes. Yep, Super Bowl, junk food heaven. What would be the starting materials, also known as the reactants? Now, if you notice for this class, I'm going to make life easy. There's one question mark here, it's just one. Sometimes there's more than one. Well, how do you do this? This is the fun part of synthesis. Well, you look at what you're trying to make, and you look at what's different. What's not a carbon-carbon single bond, or carbon or single carbon or hydrogen atom? Oh, chlorine here, on adjacent carbons. Adjacent means next door to each other. And how do we show that? Remember, X in this type of reaction could be fluorine, chlorine, bromine, or iodine. In this case, it's chlorine. And what do we start with? Well, we react some halogen with a double bond. So the 2 carbons with the halogens, these 2, have to be, when you start with, a double bond. Now, do you break carbon-carbon single bonds? No. So if you notice, I have 4 carbons total. That means the molecule I start with to react with chlorine has to have 4 carbons, and the 2 carbons with the halogen are the 2 carbons of the double bond, which would be these 2. So I'm going to put in double bond. If I take this molecule and react with chlorine, I will get that. And that's synthesis. Oh, let's do another. Well, I'll let you try one. And what would be the starting material for that reaction? And again, this is the most exciting and fun part of organic chemistry. Hope you're having fun. I am. When you're done, give me a thumbs up. Or if you don't like what I'm doing, you can give me a thumbs. Wait, Zoom never put that in there. They should have a thumbs down too. Oh, I'm going to make $1 million, sell Zoom emojis apps. I bet somebody's done that already, maybe. All right, I think everybody's done. Look at this molecule. What do you make react with bromine to make this molecule? What's different? What's not a carbon-carbon single bond or carbon or hydrogen atom? Ooh, a bromine here and an adjacent carbon, a bromine there. And I can rewrite that like this. And If I react halogen, which this is what it is, remember X can be, oh, X can be fluorine, chlorine, bromine, or iodine. In this case, it's bromine. You start with a double bond. So how do you work backwards? Synthesis. The two carbons with the halogens are the two carbons of the double bond. In this reaction going that way, do we break any carbon-carbon single bond? No. So if I end up with 5 carbons in a ring, I better begin with 5 carbons in a ring. Now, these 2 carbons here, remember a benzene line is a carbon, have the halogens are these, have to be 2 carbons in double bond. How do I show that like that? And that's how I do, oh, let's do one more. Should have moved it over further. Now, I'm going to help you out. On a test, you won't have this and I won't be helping you out. Well, hopefully I have by showing you this now. And why don't you figure out what would be the starting material for that reaction? This is a pretty sophisticated problem. So if you're having a little trouble with this one, don't get all upset. You should never get all upset in my class because I'm here to help. All right, I think everybody's done. Let's do this. If I look at this molecule, I'm going to say what's different, what's not carbon, what's not hydrogen, what's not a carbon-carbon single bond. Ooh, look, a chlorine on a carbon. And I'm reacting it with HCl, which is HX. And the reaction is, how do I put a halogen on there? I take a double bond, react it with HX, a carbon, 1 carbon of the double bond gets a halogen, and the other carbon gets a hydrogen. So notice this reaction tells me if I have a molecule, 1 carbon with a halogen, and an adjacent one connected to that with a hydrogen, those would have been the 2 carbons of the double bond I start with. Well, notice I have 6 carbons. Since I don't break carbon-carbon single bonds, I'll start with 6 carbons, I better. Now, this carbon here is this carbon with the halogen, which has to be 1 of the 2 carbons of double bond. And over here, I have a hydrogen on this carbon, so I can say that's the other carbon. And that would be your answer. Now, let me show you something interesting, because I picked this molecule for a reason. Well, what if I said this carbon has the halogen and I look at that carbon and make it the double bond. Dr. White has to do something he shouldn't right now. And then you would get that. And if you look at this carbon, there are 5 bonds to carbon. No, you can't have that. So this can never be right. And that's why this is your only product for the starting material for that reaction. And that's how you do synthesis. Now, if you look at the problem set, I don't have any synthesis problems. Bad, Dr. White. No, you take any one of the problems I give you in the answer key, cover the starting material, put down the product and the reaction, and you can do your own synthesis problems. Now, as of now, it might change in the future, but as of now, the Supreme Court of the United States has outlawed faculty from doing any dangerous or mean things to students. There's another term I use, I can't think of it right now, but anyways, junk food overdose, that causes that. But anyways, because I don't do anything to the students that are nasty and bad, I will only on test 1 put 1 synthesis problem. If I did more, it would be, I know what the term, Supreme Court has outlawed cruel and unusual punishments to students as of now. And I only will put 1 on test 2 because you lost your rookie status by then. I'll put maybe 2 or 3, never more, because that would be cruel and unusual punishment. So I can't do that, at least as of now. But when I took it for organic chemistry majors, half the test was like that. They were pretty hard. But that's if you're going to be an organic chemist, which, as most of you indicated, you're not. All right. Ooh, I bet, I don't know, let's see. I did the public service about the method already. Another thing is, don't forget, this Wednesday, the lab you did last week will be due. All right. Guess what time it is? It's new chapter time. Oh, you'll learn some life things, advice from Dr. White. Never, ever let go of the little kid inside of your brain, the little 5-year-old who loves fire engines and police cars, lights going by, not after me, but going by, still likes other things too, including my friend over here. But it's new chapter time. And this new chapter, I'm going to be able to tell you about things like wars that were held over molecules, things about Napoleon, things that taste real good, make your food taste good, and one of the most famous dreams in all of organic chemistry, or even I think chemistry. All that in this chapter? Of course. All right, everybody see chapter 4 on your screen? Thank you. All right, this chapter 4 deals with aromatic compounds. And aromatic compounds have been around for eons. They're named aromatic compounds because they're originally isolated from spices and herbs. An example of this is vanillin. Another one is cinnamon, is also. And by the way, Dr. White loves vanilla, like a vanilla extract, and that comes from the vanillin bean, which you get that taste from aromatic compounds. Remember, I told you organic chemistry is everywhere. Oh, I forgot to ask. Did anybody drive by a gas station and think of alkanes? Did anybody happen to look at a candle and think of alkanes? Oh. I'm even doing oi. If you don't know Yiddish, oi means oh, but more than that. Uh, did anybody happen to think of when you were cooking with gas or your house was nice and warm? I see one person. How about the rest of you? Did anybody happen to think of that's methane? That's an alkane? Look out. Oi, veis mir. That's Yiddish for oh, woe was me, but it means way more than that. Oi, veis. You didn't? Well, you should. Organic chemistry is all around us, and it won't hurt for you to think about it. All right. Now, interesting thing. Back in the 15, 1600s, 1700s, the major European countries were at war. And one of the driving forces of that war was aromatic compounds. Yes, they were. Now, there's a great book called Napoleon's Buttons. In fact, I was thinking about it this morning. I haven't read it in a couple of years. Great books. I always go back and reread. My favorite is Shogun and the Foundation trilogy by Asimov. They're like good friends. I go back and visit them every once in a while. And the book Napoleon's Buttons, that's a weird name. And these two really great Canadian authors wrote it. And the reason they call it Napoleon's Buttons is, whether it's true or not, but a lot of people think it might be, one of the reasons Napoleon lost in Russia was the buttons on his soldiers' uniforms, their overcoats, were made of very cheap metal material. And in the cold weather, they got friable. That's a fancy word meaning they break real easy. And it's sort of hard to find if you can't keep your coat closed to keep you warm. And that's why they call it that. But it's a great book and it has a number of areas about how certain molecules, most of them are organic, affect the history of mankind. And aromatic compounds are in there. Now, if you think about it, how many of you are familiar with Columbus? I think you've heard of Christopher Columbus. And what was he doing? How did he find America? Well, he wasn't looking for America. He was looking for a shorter route to India. India. Why? Because that area had spices. And back in the 14, 15, and 16, 1700s, they didn't have refrigeration. So next day, or even the first day when you're cooking food, to make it taste better, you put in spices like cinnamon and others. And you got those from the Middle East and India. Well, that's a long trek over land. How can you shorten it by sea? And Columbus, along with many other explorers, were looking over shorter ways. Well, he went the wrong way, found America, unless you also believe that the Vikings were here first, which I sort of believe too. But actually, the indigenous Indians were here before that, and where they came from, that's history. And cloves is another example of aromatic. We'll actually do a lab with this stuff. And but anyways, if you think about the first land he landed and found, he called East Indies. Why? Because he was going east and he thought he was in India. He was, boy, was he lost. But true story. So many spices, especially in the Asian area basin, European powers fought over for control of that land because of control of spices, which also meant money because people wanted them and they paid a lot of money for them. So that's what we're going to talk about. Ooh, that reminds me, I forgot to say one thing. I don't get any kickbacks from them, but let's go to the internet. For many, many years, I've been buying from the Spice House. They have one in Chicago, one in Evanston. There used to be one way west suburbs but they sold that one. And students told me, don't go back there. But anyways, and they do ship by UPS. And this is the best place in the world to get spices. When I used to go to the Evanston one, I don't now, I got lazy and I just have them ship at UPS. But I've been in there where I've been introduced to some of the top chefs in Chicagoland who buy their spices here. Why did I get introduced? Because years ago they had a balance problem. I happened to be in their store and I showed them how to fix it. Chemists know how to deal with balances. But anyways, they have some of the best things. Hang in there while I find it. Everybody see the bottle of pure vanilla extract? This is their double strength Madagascar vanilla extract, and I've been buying it for many years. You notice it's expensive. I usually buy an 8-ounce bottle. Dr. White's a vanilla junkie. I like putting it in water with a little sugar. I like cooking with it. And this stuff, once you try this stuff, the stuff you buy from the supermarket is just total garbage. So this is the best place to buy it, and it's worth every penny of it. All right, if I look at the clock, I've gone over 2 minutes. I'm sorry. Let's take a break. I'll give you an extra 3 minutes. Why don't we come back? Well, let me go another minute or two more, and then we'll take a break at 1:55, and we'll take a 5-minute break. So I'll go a couple minutes more. Dr. White got excited about vanilla extract. Oh, I should mention also here, they have some of the most dangerous, I have the best cumin you'll ever buy. Uh, this is another one of my favorites. Commercial from the Spice House, ground chipotle chilies. Oh, I love this stuff. I usually buy a couple of the half cup. They used to sell it by the pound, which was quite not was not cheap. But I get the 4-ounce bag. I don't buy the jar because I know how to refill it. And there's one other one that's a favorite but very dangerous. They also have ghost peppers, which I haven't. Everybody see the ground habanero powder? That's dangerous beyond dangerous. It's hotter than hot, and it's great. In a big pot of chili, like about 2 gallons of chili, just go tink, tink, tink. I actually have micro spatulas to put in a little. Later on in the semester with ground habanero, I'll talk about one of the dumbest things I've ever done in my life and how knowing organic chemistry saved me. With that, it's time for a break. I'll see you in 5 minutes. I'm going to go stretch, and I'll be back in 5. For those who are wondering, this picture right here you see on your screen for me, that's called a condenser, a small condenser head for what's called bantamware. And this is a picture of what I used in grad school. I actually have one I got a couple of years ago on eBay. And I use this a lot, and I'll teach you more about condensers. Brand new, these cost about $150. All right, let's get back to work. I was talking about aromatic compounds in the chapter here. Now, aromatic compounds have a unique quality, and it's a chemical property. They're very stable. They don't change with time. They don't go rancid, and I'll teach you later on, rancid is from oxygen reacting with certain, actually double bonds and certain things like fats and oils. They don't change, and they stay pretty stable. And many of them have what's called a C6H6 ring, otherwise known as an aromatic ring. So let's continue on. Now, when we talk about aromatic compounds, the simplest structure, simplest aromatic compound in organic chemistry is benzene. And benzene is a liquid at room temperature. And one of the greatest of all organic chemists or chemists in general, Kekula, proposed the structure for benzene. And he was the first one to get the right structure. He's one of the greatest of all, and he came up with a reasonable structure, which is now still being used for benzene. And once he did that, that helped explain aromatic compounds in general. Quite a great achievement. Now, this alone would have been a lifetime achievement, but he did a few other things. I'll talk about the snake dream in a second. But he was one of the first chemists to realize that carbon should only have 4 bonds to it, otherwise known as the tetravalence of carbon. Remember, 4 bonds to carbon. He was also the first one to recognize that carbon atoms are connected together by chemical bonds. And he determined that benzene contained 3 conjugated double bonds. Now, what do we mean by that? Well, how do you draw a ring that has 6 carbons in it and 6 hydrogens? Cyclohexane has 12 hydrogens and 6 carbons. This can't be benzene. Well, Kekula came up with the concept, the one way of drawing it is benzene, which is one way organic chemists draw it, has a 6-membered ring with 3 conjugated double bonds. I'll never ask you what it means conjugated, but you should know that means alternating double, single, double, single, double, single, and that's conjugated. Now, how did he come up with this idea to solve this problem? Well, later on in his life, he was at the symposium and he was asked by one of the people, how'd you come up with the idea that benzene is a 6-membered ring with 3 conjugated, and I'll abbreviate, double bonds? And he said, I had a dream. And the night before I came up with the idea, I had a dream where a snake was chasing his tail. And it caught it. And it caught the head, caught the tail, and was going in a circle. And next morning, I remembered the dream, and I came up with the idea. It showed me how to do benzene. And that's the story he tells. And if you look at this, here's a stamp with a picture of Kekula. I love that beard. If it wasn't for the fact, well, I don't do it as much now, but even now with people wearing a mask, you don't want a beard like that because you'll break the seal around your mass. And when I go to chemical companies or if I go in a place where I might have to put on a mask, or worse, I have an air tank on your back with a mask, you don't want a beard like that because that will break the seal of the mask and you're dead. But obviously he didn't have to. And this is a stamp. It's a 25-cent Pfennig stamp, penny, Pfennig in German, from 1979. It's from a country that no longer exists, DDR. DDR is Deutsches Demokratisches Republika, which is otherwise known as East Germany. And it shows you when Kekula lived, and it has a picture of benzene on it. And about 2 years ago, a student of mine in 170, because up to then I said, if anybody sees where I can get it, I'd buy one, said, it's on sale on eBay. What else not on sale on eBay? And I was able to get 2 of them for about $5. I was shocked how cheap it was. And I now have mounted in a nice picture in my living room. I'm an organic chemist. And this is Kekula. Now, Kekula's model for benzene uses resonance. And resonance is when you move only electrons in a molecule, not atoms. That's called resonance. Switches off for this in terms of the term Kekula. Now, normally, but I went overboard on this, you usually put brackets, you don't have to, because these are never isolated. They exist at the same time. And you show resonance by a double-headed arrow. This is not an equilibrium. This is resonance. Now, the arrows in here show where the electrons are moving. Remember, each double bond is a sigma bond and a pi bond. And the electrons are moving. Remember, each line are 2 electrons are the pi bonds. And these are double-headed arrows. All right, next 2 slides, 3 slides, will this be on a test? Everybody see me in the upper corner? Click. I just turned the switch. Will this be on a test? Off. Now, when we talk about benzene, the p orbitals, remember a double bond, is 1 pi bond and 1 sigma bond. And I think I showed you, but I'll do it now. Each carbon, the pi bond, I think I have a better picture, is overlap. And this is the pi bond. And these are the p orbitals. Switches off, but it's still important to understand. And they exist both above and below the carbon. And when we look at a benzene ring, here is each carbon of the benzene ring right here. And here's the p orbital. And each one has 1 electron. And an orbital is the area in blue. If I could stop all motion, well, I wish I could do that, but nobody can, including moving electrons. In this blue area here or here, I'd find this electron. And same thing here. Well, they can share, overlap, and this is what a pi bond is. Now with benzene, since you have all these together in a ring, conjugated, you can have all of them sharing together. How many of you have ever seen kids in a circle holding hands and do the ring around the rosy, all fall down? Have you ever seen that or done that when you're a kid? Well, think of a benzene ring as all the carbons holding hands in a ring going around, but they don't do ring around the post. By the way, if you ever want to look at it, look up all the words for that. And ring around the rosy came from the Middle Ages and the Black Plague. Interesting. But anyways, they hold hands and they're very strong. And if I were looking, do I have it? All right. Now, if you were happen to be looking here, here's your eye, and you're looking down from the top, it would look like this. all you'd see sort of like a donut, looking down at the top of a donut. Well, it turns out, I'm going to come back to the slide in a second. How do we draw benzene? Now, these are the molecular structures, and I can draw benzene, and this you should know. The structure for benzene, one way to draw it would be this way. Oh, that's an ugly looking ring. Or I can show the other resonance form. No, I've moved. Or I can use this one, the delocalized pi cloud, which is a ring with a circle in the center. Now, I like to do one of these two because I just think it looks cooler than this. On a test, any one of these three are correct for benzene. All right, let me go back to this. Now, how do you know if you have an aromatic ring, which is called aromaticity? Any cycloatomic, that means any ring with atoms, and you can have other atoms besides carbon in an aromatic ring, have the following formula. The switch is off for this, but sometimes I've heard they ask this question on entrance exams, like nursing. I've never taken it, but people have told me. 2n plus 2 equal number of pi conjugated electrons. Now, if we look at benzene ring, each double bond is 2 pi electrons, 2, 4, 6. So benzene has 6 pi electrons, and when n is 2, 2 times 2 plus 2 equals 6, and that's how you can tell this is aromatic. I will never ask this on a test or the final, but other people do, so you should know about it. So this is a symbol for benzene. Now, let's talk about the nomenclature of aromatic compounds, because I don't think I've mentioned this. I might have. On Monday, I'll talk more about it. Because if I remember correctly, I think a week from this Wednesday is test 1. I'll talk more about it on Monday. But my test, like the practice problems, there are 3 areas. One is what I call general knowledge, like how many bonds to carbon? Hopefully I'll know 4. Another one is nomenclature, names. And names would be, here's a molecule, give the IUPAC name, or here's a name, draw the structure. And the third one is give the reactions, give the reaction products. But one problem on test 1 will be give the starting material. That's all reaction. So let's talk about the nomenclature of aromatic compounds. Now, it turns out benzene has been used for eons. I'm talking eons. And IUPAC, in their infinite wisdom, said, we're not going to get these organic chemists to change. This has been used. So the IUPAC name, which is also what I'll tell you is the common name, is for this molecule is called benzene. Common mistake, students who didn't learn the structure put down cyclohexatriene, wrong, it's benzene. And you can draw benzene this way. By the way, my software does a nice job of drawing rings. You can draw it this way, which is another resonance form, or you can draw it this way, which I don't think looks cool, but it's fine. This is benzene. Note, if you draw this, I'll give you 0 points if I ask, draw the structure of benzene, because this is cyclohexane, which is different as night and day from benzene. It's like if on a test of the A and P, anatomy and physiology, say draw the hand and you draw a foot, should I give you partial credit for that? No. And so remember, when you draw benzene, it's important to put either into bonds or a circle for benzene. If you don't, that's cyclohexane, then I'd take off points. On test number 1, the reason I'm telling you this, more than once I've had a student forget to put those bonds in there or the circle, and they've lost 10, 15 points. It's, I don't want to say stupid. It's not, it's a painful way to lose points on a test. And boy, they were in pain. They were upset with me. I said, I warned you. I'm warning all of you now. When you do benzene, make sure you show the bonds or a circle. So this is benzene, and you should know it. Now, when you put a methyl group on a benzene ring, we don't call that methylbenzene. This also has been around for eons, and this is called toluene. And a methyl group on a benzene ring, how do you draw toluene? Either this or this form, resonance form, or it's a methyl group on a benzene ring. And it's called toluene because this has been around for ages also. And again, IUPAC said, we will not change those organic chemists. We'll use the word they're used to, and it's now the IUPAC name. Now, another molecule, which I will not ask you to learn the name of, but I thought I'd mention it, is styrene. And styrene, how many of you have ever heard of polystyrene cups or coolers? It's made from styrene. That's how poly means many. And a vinyl group, I talked to you about this briefly, you didn't have to learn the name, but a vinyl group on a benzene ring, common name in IUPAC is styrene. This I'll never ask on a test, but I just thought I'd mention it briefly. But you should know toluene and benzene. Benzene, 6-membered ring with 3 alternating double bonds like this, or this resonance structure, or you can use the pi cloud, delocalized pi cloud with the circle. And toluene, benzene ring with a methyl group, benzene ring with a methyl group, benzene ring this way with a methyl group. Now I have this is a sad story to tell you. Until organic chemists came up with latex paint, which only uses water as a solvent. I painted some of the rooms in my house, my garage, and it makes life very easy. Before that, in the 30s, 40s, and 50s, they didn't have latex paint. And what they used were pigments in various organic solvents. And 2 of the more common ones was benzene and toluene. Unfortunately, benzene and toluene have severe negative effects on your body and the organs in your body, including your brain. And when I was young, one of my mother's 2nd or 3rd cousins, he had been a painter all his life. And by the time I met him, he was in his late 50s, early 60s. And he was about, and this is very sad, about 1 step up from being a vegetable. The fumes from the paint and being in rooms with those fumes got to his brain and other organs in his body. It was very sad. And how many of you have heard, and luckily I've never met, and I hope I don't, but anybody who's sniffed glue? And the same thing happens. And why? Because the older glues, and I don't know if some of them still do, had either benzene or toluene in them. What they were really sniffing was the toluene or benzene. And that rotted out their brains or whatever. I'm not a medical doctor. In fact, how many are familiar with the product liquid paper? For a number of years, liquid paper used to have toluene in it. People were sniffing that. And they'd get a high out of it and also destroy their brain. I think luckily they've taken that out and reformulated. But I just thought I'd tell you, there's good sized organic chemistry and not good. Now, when we have more than one group on a benzene ring, we use numbers, but a lot of with just two groups, we use something called letters, words, which I'll talk to you about in a second, ortho, meta, and para. But before I do that, let's go to this slide. I'll come back to the others. One of these days, I'll change the order. Here's some new substituents. You know about methyl, ethyl, and propyl, isopropyl, and butyl, T-butyl. Here's, excuse me, some more I want you to learn. If you have a chlorine atom on a benzene ring, that's, and also on an alkyl group or alkanes, cycloalkanes, but they're not that useful, and that's why I didn't go through. It's called the chloro group. Bromine is called bromo. Iodine is called iodo. Fluorine is fluoro. By the way, I always get these O's and U's mixed up, but NO2 group is nitro. Now, this one you don't have to know, but I'll teach you later. It's important. Sulfonic, SO3H, and that group on a benzene ring is responsible for how we can get our modern laundry detergents. So if you like clean clothes, having a sulfonic acid group on a benzene ring, which is then further reacted, helps get your laundry detergent or the key molecule in Tide, All, and whatever other brand you're using. And as you know, other alkyl groups. So the ones you should know are chlorine on something is chloro, bromine is bromo, iodine is iodo, fluorine is fluoro, and NO2 group, and the bond is to the nitrogen, not the oxygen. Don't forget the old two, is nitro. So what does this mean? Give the IUPAC name for the following. What do I have? Oh, look, it's a ring, but it's got three conjugated double bonds. 1, 2, 3. That's benzene. It's got a bromo group on it. It's bromobenzene. And that's how you do it. Remember, on a ring, when there's only one group on there, you don't use a number, no number. And you learned that for cyclohexane. Similar. Oh, let's do another one. Cl chloro. Your turn. How would you name that? And when you're done, give me a thumbs up or smile. And maybe next week, if I get it done, you'll have the new app that can do a thumbs down in Zoom. Don't hold your breath. Anyways, oh, look, it's a benzene ring. 6-membered ring with 3 double bonds conjugated and a chlorine atom. And chlorine is chloro. And if you're typing this is all lowercase, but if you mix them, which I do, when I write, I won't take points off. Well, let's do one more, and I'll do this one. And NO2 on a benzene ring, this is called a nitro group. So this would be nitro benzene. And that's how you do this. And let's go back to a slide I had that on. And once again, it's time for Dr. White to be subtle. Hint, know this. I didn't do a file for it, but you should know what's a chloro. Chlorine is chloro, bromine on something is bromo, iodine, iodo, fluorine, fluoro, NO2, nitro. I won't ask you to learn sulfonic, but we'll talk about it later on in the semester when we get into detergents, which we will cover in this class. Now, let me back up. When you have more than two groups on, or only two groups, organic chemists drew eons ago, instead of using numbers like you do on cyclohexane, for benzene rings, you use what's known as ortho, meta, and para for di-substituted isomers of benzene. And these special names are used in my class on the test instead of numbers, because all organic chemists do that. And let me show you how that goes. Everybody see my whiteboard? Thank you. If we were in class, this would take a little while. Let me get the right colored pen. And if you look on your screen, you'll see I have three molecules I've just drawn, and they're all isomers. Isomer means they have the same number of each atom, in this case, carbon hydrogens, and the only difference is how they exist are connected together. And I'll be patient while you write them all down, if you want, or you look at the videotape later today. Don't forget, I'm keeping up to date. I have my YouTube channel. Tonight at midnight, I'll be giving speed drawing lessons. No, I won't. If we were in a classroom, I could look around and see everybody writing furiously on their paper, their notes, and tell when everybody's done. And when you're done kind of copying these down, I think everybody's done. All right, let's look at each one of these. Notice I have a benzene ring and an ethyl and an N-propyl. So this would be ethyl, N-propyl, benzene, Times like this, I wish I could do a copy on this. This would be ethyl, again, ethyl group, and propyl. Remember, 3 carbons to the N carbon. Benzene. And this last one would also be ethyl and propyl. Benzene. Now, over here, let me put an important thing. I was sort of tilting because junk food overdose. No, it's just. Now, these are the 3 names organic chemists use only for benzene toluene aromatic rings, not cyclohexane, ortho, 1,2 disubstituted. Now I'll show you what this means. Meta, 1,3 disubstituted, and para, 1,4. Look out, I'm going Technicolor. If I call this carbon 1, the F and propyl group is on carbon 2. If I call this one, the N propyl is on 3. If I call this one, it's on 4. And therefore, isomer A, how do we name that? This is ortho ethyl and propyl benzene. Ortho, why? Because it's 1,2 disubstituted. Again here. Now, if we look here, we're 1,3 disubstituted, and 1,3 is meta. So this would be the meta isomer. And the name for that is meta ethyl and propyl benzene. Meta, 1,3 disubstituted. And finally, over here, the name of this, it's 1,4 disubstituted, would be para. So this would be para ethyl and propyl benzene. 1,2 disubstituted, ortho. 1,3 disubstituted, meta. 1,4 para. And we're talking about, if you have call one of the groups 1, what's the number going clockwise or counterclockwise to give it the smallest number? And that's how you determine this. Everybody get the hint? You should know ortho, 1,2 disubstituted. Meta, 1,3 disubstituted. Para, 1,4. And if we look at this molecule, I'll do this one, then I'm going to let you have some fun. What would be the IUPAC name for that? This is 1. This is on 2. It doesn't matter. So it's disubstituted. It's 1,2. So that would be ortho. It's a benzene ring, a 6-membered ring with 3 conjugated double bonds. 1, 2, 3. Remember alternating double, single, double, single, double, single. And I have on there an ethyl and chloro. Chlorine is shown by chloro. And it's 1, 2. Therefore, it's ortho. So that would be orthoethylchlorobenzene. Ooh, say that 5 times quickly. And why don't you try this one? 3 points each. Give the IUPAC name for the following. And when you're done, give a thumbs up. All right, I think everybody's done. Let's take a look at this. What do we see here? Oh, look, a 6-member ring, but it has 3 double bonds and they're conjugated, alternating single, double, single, double, single, double. By the way, I've never seen a non-conjugated ring with double bonds. I don't think you can have it, but anyways, so immediately I say, I better give myself more room. A benzene ring. And, oh, look, it's di-substituted. It has a T-butyl group. You can call it TERT. Dr. White's going to be a lazy organic chemist. And it's got an isopropyl group. And they're 1, 2, 3. 1, 3 di-substituted. And 1, 3 is meta. So that would be meta T-butyl isopropyl benzene. Let's do one more. Got it, huh? And why don't you do this one? Cl chloro Br bromo, in case you haven't learned that chart yet. Cl chloro Br bromo. Boy, time flies when you're having fun with aromatic compounds. In case you haven't learned it, remember 1, 2 ortho, 1, 3 meta, 1, 4 para. I think everybody's done. So let me move on. All right, what do we have here? A benzene ring. And we have a chlorine and a bromine. The root name is benzene. Remember, that's not cyclohexatriene, which students try and do, and I'll mark it wrong. I have a bromo and a chloro. And notice this is 1, this is 2, 3, 4. If I call this 1, it's still, and it's 1,4 disubstituted. And that's para. And that would be para-bromochlorobenzene. Now, let's do one more. This one you don't have to write down. Does everybody know what I just wrote on the screen? It's paramedic. 1,4 para medic. Yep, it's pretty bad. You can groan and moan too. Yep, paramedic. All right, now let me teach you something important about this molecule and its nomenclature. This, as I've taught you, is toluene. I can see some of you still love that paramedic. You can show that to your friends. No, they won't get it. Well, anyways, let's look at this molecule. And this is toluene with a bromine on it. But IUPAC considers this disubstituted. Even though the methyl group is in the name toluene, it's disubstituted. The methyl group is 1. This would be 2. So the name of this would be bromo toluene but 1, 2 would be ortho. So it's a little trick. Even though the methyl group is in the name toluene, it's still considered disubstituted, and you use ortho, meta, and para. NO2 is nitro. What would be the IUPAC name for that? Oh, by the way, next segment, I'll have something very explosive to talk about. If you notice, now we're just starting to get into more juicy, good stuff. Vanilla extract, cinnamon. How many of you like cherries, like the smell you can smell in Dr. Pepper, or in almonds, the smell of taste of almonds? That's, I'll teach you later on, is due to an aromatic compound. Remember, organic chemistry is everywhere. And when you're done, smile or give me a thumbs up. All right, I think everybody's done. Everybody done? Yep, you're done. Let's look at this. Oh, look, I have a nitro group, but I have a benzene ring with a methyl group on it. I know that's toluene. And this is nitrotoluene. Yeah. That was Dr. I was going to write a nitro group, use English, nitro. And notice this is 1, 2, 3, 1, 3. If we were in a classroom, I'd have this on the board so you could see it. 1, 3 is meta. So this would be meta nitro toluene. If I look at the clock, it's time to take a break. Actually, I went a minute over. So let's come back at 2:51. Take a break. I'll see you at 2:51, 5 minutes from now. I'll see you back in 5. And let's get back to work. All right, I'll ring the bell, ring, 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 ring. Everybody back like the school marm used to do. I like that school marm. School, yeah, that's what they called them. All right, everybody back? It reminds me, I can't do it today, Wednesday. I'll try and remember this great cartoon about teaching on Zoom I'll have to bring. And it's G-rated because I even sent it to a dean. All right, now we were talking about, no, the exam isn't this Wednesday. Hold on, it's a good question. Let's find out something. If I have it this Wednesday, guess what? I made a mistake on my syllabus. Oh, give me a break. Hold on 1 second. All right. I did make a mistake. Well, that happens. All right. Martin, first of all, thank you very much for bringing it to my attention. I would have noticed that there's no way I'm going to finish this up. And if I haven't talked to you about it yet, I think I mentioned it, but I better mention it again. Dr. White teaches by my golden rule of teaching. And that is, I don't do to my students what I didn't like done to me when I was a student. And I sure didn't like learning about stuff a day before the test and have to master it to do well on the test. I had one instructor who did that. We got him fired, but anyways, that's another story, another day. So guess what? I made a mistake. And if you notice, it says tentative, not exact, because sometimes I do make a mistake. We will have our test number 1 a week from this Wednesday. I'll put out an email to that effect. And you have my word on that. Before we get into everybody, thank you for doing that. And now, quick thing, don't forget tonight, Monday, and also on Wednesdays, I have my office hour. If you want, stop by the office hour tonight. If you have a chance, I've asked my class at COD to do that too, because I'm looking for volunteers to help me experiment, actually practice using the breakout rooms in Zoom, because this Wednesday in lab, I'm going to try that. And this will give you an opportunity to meet and talk to your classmates, and for me to come in and say hello to, and for you to talk to me if you want to on an informal basis. If we were in the lab at ECC, I'd be coming around talking to you and get to know you. Unfortunately, we can't do that online, but this is an experiment I'm going to try. Dr. White's organic chemists who do experiments, including with your brain and you. All right. Again, thank you. The test is not this Wednesday. I haven't finished everything on test number 1 yet, which aromatic compounds will be. All right. Now, we were talking about nomenclature, and when it's dye substituted, you use, yep, when it's dye substituted, you use ortho, meta, and para. Now, what do you do when you have more than two groups on there? Use numbers just like on cyclohexane. And let's do a molecule, an interesting molecule. Don't forget to put, remember, 2 is dye. And on this one right here, the bond is really to nitrogen, but you draw it this way. I could have, but I don't like to draw it this way. I don't like doing that. And I'll do this one. All right. Oh, a benzene ring, but we have a methyl group, and that's toluene. That's the base name. Oh, NO2 group. That's nitro. And I have not one, not two, but 3 groups. And we call 2-di, 3-trinitro. Now, it turns out this is carbon 1. This would be 2, 3, 4, 5, 6. If you want the other way, you get the same thing. So this is 2, 4, 6, trinitrotoluene. 2, 4, 6, trinitrotoluene. 2, 4, 6. Oh, it's hurting my jaw. Trinitrotoluene. Did I tell you how lazy organic chemists are? We are. And why don't I just, not for IUPAC, a T, an N, and a T, I'll call it TNT. And this is the structure of the 2,4,6 trinitrotoluene, which has the common name TNT, which is an explosive. Now, how many of you have heard of the Nobel Prizes? I think most of you have, right? And how did they come about? Well, a gentleman called Alfred Nobel set up a foundation, put in a lot of his money. He was very rich, and that created the Nobel Prizes. There's one for chemistry, there's one in physics, one medicine, one peace, and I'm not sure if I'm probably missing one. Is there one for English? I don't know if there's one or not for writing. But anyways, how did Alfred Nobel get rich? Well, he and his brother found out TNT and also trinitroglycerin are very explosive. This is a liquid at room temperature. And if we were in our lab or in our classroom and I had a bottle of TNT and I went like that, we'd all be dead now because it's very shock sensitive. And think about transporting things in the late 1800s with a horse and wagon. You had a lot of dead people. Well, they found how to use nitroglycerin and trinitrotoluene. They mixed it with clay in a certain way, and don't try this ever at home. I won't. And then they could put a blasting cap in it or another way to explode that because they made it. And they made sticks of this and they called it dynamite. And they got quite wealthy. How did they get very wealthy? Well, not from mining. Turns out you could make very powerful explosives with their method that was used by the military of various companies or countries in the world. So Alfred Nobel and his brother made millions from selling explosives for munitions for war. Now, sad story. It was still quite dangerous doing that, and it still is today. I wouldn't work in a plant making nitroglycerin or trinitrotoluene. No, I like having my brain and my head on my shoulders, but it's still safer than it was before. And unfortunately, when they were doing this, one of their plants did blow up and it killed his brother. But he took some money and started the Nobel Foundation that gives out the Nobel Prizes. So think about it. The Nobel Peace Prize is funded or was originally funded by money that came from the sale of explosives to military. Now, is there anything wrong with that? In my mind, no, but it's an interesting side story of organic chemistry. And let me let you have a try for one. Why don't you try this one? What would be the IUPAC name for that molecule? Thank you. Isn't there an arsenal near Highway 6 going south on off the Stevenson, getting off at Highway 6, somewhere around, isn't it called Arsenal Road or something? And that was because they had a big arsenal there. All right, looks like everybody's done. I better get to work, or I'm going to have some upset students, and you don't want that. All right, benzene ring, methyl group, toluene. I have a chlorine here. This is 1, 2, 3. I have a chlorine there. Dichloro. And therefore, since I have tri-substituted, this is considered a substitution, I would call this 2,3-dichlorotoluene. Oh, let's do one more. And why don't you try this one? What would be the IUPAC name of this molecule? It's going to be long. I think everybody's done. Is everybody done? Give me a thumbs up if you are. All right, I'll give you, looks like everybody's who can do a thumbs up is, and let's do this. All right, notice I have a benzene ring. So the root name is benzene. Next, I have an ethyl group, N-propyl isopropyl. And therefore, this would be ethyl. Now, there are different ways you could write this because I'm not holding you to the IUPAC alphabet rule, but I will do the right one. And there's different ways you could number it, but I'll use the IUPAC. And ethyl would be 1 because it's the highest alphabetical priority. So I have N-propyl, isopropyl. This would be 1. This would be the N-propyl is on 2. And the isopropyl is on 3. This is an I. So this would be 1 ethyl, 3 isopropyl, 2 N-propyl. Now, if you have these different order, different numbers, I would accept that you could have 1 isopropyl, 2 N-propyl, 3 ethyl, even though this is the correct IUPAC way. And I always try and do that. And that's how you do nomenclature. Wait, there's only one part. Let's do the other one. And the other type of nomenclature question would be,
For the last problem,
yep,
shouldn't it be 4 isopropyl instead of 3 isopropyl?
Dr. White is suffering from junk food overdose. Thank you. I'm sorry. Well, there goes my perfect score today. All right, let's continue on. Thank you very much. And let me do the first one. Benzene. And that would be this, or this, or this one. If you do this, that's cyclohexane, which I would mark wrong. Remember to put the circle or the double bonds inside the ring. Why don't you try this one? Draw the structure toluene. If your rings don't look as nice as mine, that's okay. If they look better than mine, that's even better. All right, looks like everybody's done. Let's do this one. Toluene, that tells you have a benzene ring with a methyl group on it. Doesn't matter which carbon you put it on. This is one way of drawing it. Here's the other resonance form. And finally, if you want to use the circle, which Dr. White doesn't, but it's okay on my test, that's it. If you put a cyclohexane ring with a methyl, I'd mark it wrong. All right, let's do another one. And why don't you draw the structure for iodobenzene? And don't forget, if you want to see an instant replay of this tomorrow, check out the YouTube channel for Chem 170. All right, everybody's done. How do you decode this organic chemical name? You start from the right, move left. Benzene ring. And then iodo-iodine. And you can draw the other resonance forms here, but I'll just do one. Oh, this looks bad. And that's how you do it. Let's do one more. Remember, meta, ortho 1,2, meta 1,3, para 1,4, disubstitute benzene ring. All right, looks like everybody's done. How do you decode this? You start from the right and move left. Toluene. Let's see if I can count today. Hold on. That's better. And toluene has a methyl group. Chloro, that means chlorine. Para, 1, 4, 1, 2. Now I put the 3, 4. And this would be chloro. And that's how you do it. Remember, ortho is 1, 2 disubstituted. Meta is 1, 3. And para is 1, 4 disubstituted. And that's how you do nomenclature. Oh, let's do one more. Now we're on a roll. And why don't you try, draw the structure 2,4-dibromo toluene, bromo, Br, bromine. For those who are wondering why you might have been, or like Dr. White, spending a lot of quality time with my driveway shovel and snowblower, I heard the other day, the last 2 weeks in Chicagoland, we've gotten almost 19 inches of snow. All right, I think everybody's done. Let's do it. How do you decode this? Know what to draw? You start from the right, move left. Toluene. Don't forget to put the lines in, the bonds, or I'll mark it. That's toluene. Bromo is a bromine. Di means two. Remember, di, 2, try 3. Tetra is 4, but I've never seen it in use. And where are those bromine on carbons 2 and 4? This is 1, 2, 3, 4, 2, 4. And that's how you do 2,4-dibromo-toluene. All right, this slide, I'm turning the switch, click, will it be on test off. Now, it turns out benzene is very, very hard to hydrogenate. You've got a double bond. You should be able to add hydrogen and catalyst. Well, it's not that easy. You've got to take it to very high temperatures and react it for a long time. And the does not react benzene like it has 3 double bonds separate. There's something different in benzene. Again, switches off for the slide. And there's something different. And it's true for all aromatic compounds. And that difference is called resonance energy, sometimes known as stabilization energy. And that's the difference between the energy of a real molecule and the calculated energy of the most stable contributing structure. So if we were looking at theoretical for benzene, you'd say a ring, the energy of a ring plus 3 double bonds. Well, it turns out that's not true. The benzene ring is much more stable, lower energy than if you had theoretical calculation. And this is due to what we call resonance energy. And resonance energy is the fact, don't get dizzy, when these are all holding hands, these electrons, to form the conjugated double bonds that makes them very stable. And if you break one of those double bonds, you lose that stability, and benzene doesn't want to do that. Which is why benzene is very unreactive to hydrogen and a catalyst, because you'd break the stability of them holding hands. So what does that mean? Switches on, click, I just turned it back on. We have what's known as electrophilic aromatic substitution. Now, the stuff on the slide, I'm not going to ask you to learn, but the next slide, the switch will be on. Ooh, fancy new words. Electrophilic aromatic substitution. Well, I know what substitution is. I change one thing for another thing. Aromatic, we're talking about a benzene ring or toluene. Electrophilic. Well, electro sounds like electron, negative. Does everybody know what an audiophile is? Dr. White's an audiophile. I love my music. In fact, you can't see it over there. I have my speakers and a subwoofer in my office hooked up to stereo. I have I think I have, let's see, upstairs bedroom office stereo. I have 2 stereos in my family room, one to the TV and one in my super stereo. Then I have one in my utility room and another in the garage. Ooh, 5 stereos. By the way, my ultra best stereo, if you want to look up, took me 6 months to track it down back in the late 70s when it was reasonable. I could afford it. Now I couldn't replace it. I have a Marantz 8B amplifier and a Marantz 7C companion preamp. Those are probably the best components ever made for stereo. ever. They're all tube too. Oh, great. But anyways, audiophile, phile means lover. So electrophile, what does that mean? Something that loves electrons. I'm an electrophile. I'm looking for where there's some electrons. And where do you find them? The pi electrons on the benzene ring will attract me. Now, there's another kind of phile that gets arrested by the police, thank goodness. And I'll leave that to your imagination. So, due to resonance stabilization, you're not going to break those double bonds, but you can replace something that's on the benzene ring. And what's on the benzene ring? Hydrogen atoms. So I can replace one of the hydrogen atoms with something else. So let's look at the first electrophilic aromatic substitution reaction. Again, I won't ask you anything on the slide, but I'll hold on because I see somebody copying it. Remember, everything you see here is on in a file. In this case, the Aromatic Chapter 4 Aromatic Compounds file that's in Blackboard, the wrong school, D2L. I have both as a Word and a PDF file. Now, the first one we're going to talk about is halogenation. And in real life, I've only seen it done for chlorine and bromine, not iodine. And fluorine, no, I haven't seen it either. Now, because it's a benzene ring, unlike a double bond that's in a ring, single double bond, or a chain, you need a catalyst. And a catalyst just makes it go quicker. That's because aromatic rings are just stable and they don't even like to be substituted. So you got to help it. If you take a halogen plus ferric trihalide, you replace one of the hydrogens with a halogen. Now, you'll also get HX like HCl, HBr, but this is inorganic. And you don't ever have to show it because I asked, give the organic product or product. So let's take a look at one of these. And if we look at this one, question is, what's the organic product or product for this reaction? Oh, I've got a benzene ring. I'm reacting it with chlorine, which is a halogen, and I have a catalyst, ferric trihalide, where X in real life is bromine or chlorine. In this case, it's chlorine. And I replace one of the hydrogens, which we don't show, on the benzene ring. Don't forget to put the bonds in, because if you don't, that's cyclohexane and 0 points. Therefore, the answer here would be chlorobenzene. And that's how you do it. Again, you do not react the double bonds in the ring for reactions of benzene because you just substitute the hydrogens. I don't have it on there, but there would be a hydrogen on each carbon. Remember, 4 bonds to carbon. And this is C6, H6, yeah. And why don't you try one? And here's one for you to try on your very own. What would be the organic product or products? I tell you, organic chemists really discriminate against one group that's inorganic. We don't like it. All right, looks like everybody's done. Everybody done? All right, what do we have? Ooh, we have a benzene ring. What are we reacting it with? Halogen. And notice we have a catalyst, ferric trihalide. X can be bromine or chlorine. Replace one of the hydrogens with a halogen. And don't put X2 or there, just one halogen. What's X? Bromine. Therefore, our product will be this. Common mistake, students will put a 2 there, and I'll mark it wrong, because it is. Don't forget this, if you put it down, and a student did this and lost 3 points, this is bromocyclohexane. That's not what you get from this reaction. Well, that's how you do it. Let's look at this once more. What if I had this on here? Say I had a group called Z, whatever Z could be, nitro, chloro, methyl, whatever. Organic chemists usually use Z when you're talking about a benzene ring. And I was reacting with chlorine and ferric trichloride. And here, the general reaction would be this. That's better. And you'd get this. So if I had, in this case, I have Z, I have my benzene ring. Now, where do I put this chlorine? I could put it here, I could put it here, and I could put it here. If I put it on this side, this is equivalent to this side. I just rotated it. If I put it on this side, and I'm not indicating, let's call this A, B, B, and this C would be different. I could put it anywhere. If you notice, I have 1, 2, 3 different possibilities. Because if I put A here, here, it'd be the same, B, B, here would be the same. So there's 3 possible isomers. Now, it turns out, depending what Z is, will tell you where that chlorine goes to. And Z is called the director. Now, I could spend the next week teaching about directors, and you still find it a little challenging. We'll do a lab in that, but in this class, since we only have 16 weeks, I'm going to omit directors in the class. Yay, Dr. White, you're welcome. But we'll talk about it in the lab. That means I've shown you every reaction I could do with halogenation, because I'm only going to start with a benzene ring. If I had something on a benzene ring, I have to teach you about directors. And I think if you remember the first day, I found out that none of you are going to be organic chemists, which I understand. If you were, you wouldn't be taking this class, you take the 2 semester. And therefore, I'm not going to waste our time on directors when I could talk about things you might be more interested in, like proteins, carbohydrates, and other things, detergents, and soap, all the good things in our daily life, because you're never going to use a director. In fact, I've never worked in that area of organic chemistry industrially where we use directors. I have worked with benzene rings in organic chemistry. I'll talk more about that. So what that means is On test number 1, I can either give you this reaction or this reaction or this reaction for this general reaction. So you know what that means? It's time to move on to the next general reaction. And that's nitration. Everybody see it on the screen? What an NO2 group? Thank you. And nitration is where you take a benzene ring and react it with, this is nitric acid, and this is sulfuric acid. And what you do is replace one of the hydrogens with a nitro group. Now, can I give you another example? No, because the general reaction is the only reaction I can give you on test 1, because I'm not teaching you directors. We will have a lab with directors in nitration, and it's really fun when we do it in class in the actual ECC, but we won't. Now, one thing I do want to point out, let's look at H2SO4. That's usually a H plus catalyst. Remember, acids are proton donors, H plus. Let's look at nitric acid, but react it differently. By the way, this stuff will never be on the test. It's even in writing on your screen. But students get confused here, and I like to show the following. This reacts with nitric acid. The sulfuric reacts with the nitric acid, HNO3. I've just drawn it differently here, and gives you this intermediate. I'll put it in brackets because you can't isolate it. Now, if you look at this molecule, and if we were in a classroom, I'd use my hand to cover something. But if you look at there, oh, look, there's something interesting in there. Let's see, 2 hydrogens, oxygen, 2 hydrogens, oxygen, H2O. What's H2O? Water. And let me get the right color. And whenever you have a stable leaving group, and water is pretty stable, says, goodbye, I'm out of here. And the minus H2O means this leaves. And what you get is this. This is called the nitronium ion, cation, and it attacks the benzene ring. And that's how you get the nitro group on there. Now, unfortunately, I only have 1 semester, so I don't have time to go through. These are called mechanisms, how things react to form things we use, and then further. But the important thing is nitration, benzene ring with sulfuric and nitric acid, and you put on an NO2 group. Common mistakes students make here are they do this. 1, they forget the bonds, don't forget that, and they do this. They see the 3 there, and they put a 3 there, and that's wrong, and I mark it 0 points, because what's actually attacking the ring and bonding to it is this, and that's why you have both nitric and sulfuric acid together. And that's the only reaction I can show you here. Wow, we're moving along quickly. Now, the next one is sulfination. And here, you take a benzene ring, react it with sulfur trioxide and sulfuric acid. And similar to what I just showed you before, you form the sulfonic acid group, and that's SO3H bonded to that. And this is further reacted to make your laundry detergent. So the only reaction I can give you on a test is the following. I wouldn't put a question mark there, but why don't you do this reaction? What would be the product or products for the following organic for the following reaction? I'll give you 10 seconds. Go. Hint, hint, hint. Time's up. All you have to do is look at the general reaction here, since I'm not doing, and the answer is, don't forget double bonds. Now, one common mistake students do, and I take off points, is they forget that hydrogen. And they see this, and they do this. I marked that wrong, because that hydrogen is very important. This does not exist anywhere. This is a sulfonic acid group, which I don't ask you to go to. Which reminds me of, as we're finishing up, quick Dr. White story. At one company, one of my jobs was to handle certain products the company made. In chemistry, when you have someone else make a product of yours, that's called toll producing. How it got the name toll, I don't know. And one of the companies we used to make, but they made it for us, was para-toluene sulfonic acid, a sulfonic acid group. And it was in Alabama, and where they make sulfuric acid or sulfonic acid using sulfuric acid. It's a dangerous plant to go in. You're in a full hazmat suit with a gas mask on and everything. And I went to inspect them to make sure they were doing a good job. I got a full plant tour. It's summer, Alabama. You're in a full hazmat suit. Not fun at all. But they did afterward because I gave them the okay. We would continue buying. We were buying a lot. They were making a lot for us, so they were happy because that meant they would make a lot of money. They took me out to lunch, and here's a quick Dr. White story. How many of you, some of you might not, oh my God, I just did a generation. How many of you remember the scare right before 2000 of the Y2K? And that was when we turned the century, or going from 1999 to 2000, everybody's worried about, did Bill Gates and other computers do things right for software? Is that the end of the world because all our power plants are going to shut down and everything else? I mean, there was a mania going on. People were scared. I had neighbors who were stocking up on wood and everything. And I didn't really, I bought some candles just in case I needed them. But I normally have stuff because I believe in being able to survive on your own for a couple of days. So anyways, here I am in Alabama. They're taking me out to dinner, and it's in the suburbs. We're on the toll road or a highway. And I see this big billboard. Now I knew I was in Alabama. It was for a gun show. And the gun show was the Y2K gun show. Buy your guns so you're prepared for the end of mankind. And it was on the actual billboard. That's a true story. I still remember it. What was that? It was June or September 1999. So that's over 20 years ago, and I can still picture the Y2K gun show. Amazing. With that, I think I'm out of time. I hope you had a fun day, enjoyed organic chemistry. Remember, test is not this Wednesday, a week from Wednesday. I'll put out an email to that effect. Don't forget, if you need any help, come to my office hours tonight at 6 to 7:15 on a different Zoom login. It's in the syllabus. It's on D2L. And also Wednesday, don't forget to hand in your lab that's due this Wednesday, the one you did last one. Sometime tomorrow, I'll post a new assignment for next lab, which will be Alkanes and Alkynes. It's fun. And I wrote it, so I'm sort of biased. And with that, stay warm, gang gazoon. Goodbye. Goodbye.
I had a question.
Hold on.
Are we gonna have like a review before the exam?
Yes, we will. That's a good question. That will be next Monday. I'll do my world famous review for next test, which in this case is the first test. I do that for every test. And if you look at the syllabus, you'll see that in the syllabus, the last week of class, I have the whole week set up for review for a whole semester. And that's why my students do good on tests and the final, because they have review and also do the practice problems. Okay? Anybody else? If not, V for victory, stay warm. Notice I have my, it's cold out there. They don't make these anymore at LL Bean. I've got about 8 of them for real cold weather. I stocked up when I heard they were stopping to make it a number of years ago. These things are super warm. With that, stay warm. Have a good next day or two. I'll see you on Wednesday. Gang gesund. Be healthy.